It's a great pleasure to have Professor Deepak Dhar, who will be telling us about hard rotors on a lattice. Over to you, Professor Dhar.
Okay. So I'm very happy to have this opportunity to give a seminar here, and thank Nishant for organizing it. So in this talk, I will try to tell you about some recent work on hard rotors on a lattice. I will explain what these words mean. But this work is done with Julian Klamser at SPC Paris, and Saryal, who was a student here, who just finished his PhD, and Sadhu, who is at the Mumbai campus of TIFR. And some of this work is already published, so that these references are given. And some we are trying to write up and will be ready in publication for about within a month or so. Anyway, so let me go on. So this is the outline. So I will start with preliminaries and motivations for this work, and take some time to do this. And then I will define the model we study. And then I will explain what is this at most one overlap condition, which is a special condition on the parameters of the model, which lets you solve the model. And in this particular case, when this AO condition holds, this model becomes equivalent to the dimer model on a lattice. And so this particular result is of interest, and I think it's quite elementary and seems to be powerful enough that you can explain a lot of results about this particular model in this condition. And one of the results is that you can define something like the angular. So there are, in this model, there are some rotors and they have orientations. And they are in thermal equilibrium. So if you go to one side, there is a probability distribution of the orientation of the rotors. This distribution has singularities, which are generic and of geometric in origin. And they can be understood, and they, the position of the singularities and the nature of the singularities can be determined analytically. We cannot determine the function in closed form, but we can at least determine the position of singularities and the structure of the singularities. And then I will explain that this particular model has infinite number of phases. And, so that can be generalized a little bit. And then for the people who are sort of interested in the mathematics of this, so there is a transfer matrix for this problem. And this transfer matrix has a particular structure, which is interesting when this at most one overlap condition holds. And it doesn't work as well in other cases, kind of works even otherwise, and then there is some concluding remarks. Okay, so let me start. So preliminaries. So of course, in the last 200 years, there has been a lot of work done in the study of phase transitions. And the prototypical phase transition people think about is solid to liquid to gas, which is ice melts to water to steam. And interestingly, in spite of this very large amount of work on phase transitions, intense work, we still don't have a simple model of particles with realistic interactions, which is exactly soluble and shows two phase transitions. So there are models like the IISER model, which show one phase transition, liquid to gas, if you like. And there are other models which kind of show the solid to liquid transition. But if you try to ask, can we have a single model which shows solid to liquid to gas transition? That is not yet available. Of course, one knows what are these models like. So if you take molecules with Lennard-Jones type of interactions, then in Monte Carlo simulations, one can see that an assembly of such atoms will go from solid to liquid to gas. But that is only Monte Carlo studies, and that is not really theory. So one would like to have a model in which which is amenable to theoretical analysis when we show multiple phase transitions. So that was my original interest in trying to understand these models. Okay. So now coming to this idea that, okay, we would like to have a model which shows multiple phase transitions. So one realizes that the transition from the crystalline state to the liquid state is not always a single phase transition. And in many cases, what happens is that the melting from crystalline to liquid phase occurs in stages. So in the crystal phase, there is a broken translational invariance. There is a periodic arrangement of the atoms. Of course, the atoms are jiggling, so it is not fixed exact periodic arrangement, but the average positions of atoms show the periodic wave-like structure. So there are places where they're more likely, there are places where they're less likely to be. So that's a crystalline state. Liquid phase, the 1-point distribution function is just uniform. There is no broken translational invariance. There is a mean density. And, there are some correlations between atoms, but the mean density is there. And there is rotational invariance. And the crystalline state does not show translational invariance and does not show rotational invariance. Okay, so that is the what we will call a crystalline state is something which has translational invariance broken and rotational invariance broken, and liquids which have both of them there. So if you take non-spherical molecules, these break up in stages that I already said. So these mesophases, middle phases, are called liquid crystals and orientationally disordered solids, also called rotator crystals. So out of these, liquid crystals are much more familiar to physicists because, Dijen did a lot of interest of, and many other people, Chandrasekhar included, did a lot of work on liquid crystals. But there's other kind of middle phases are orientationally disordered solids. These have been studied a lot since for about 100 years now, but they are studied more often by chemists than physicists. And I'm just trying to make the subject bring back to the notice of physicists, saying that it's an interesting problem worth further study. Okay, so what are orientationally disordered solids? So in liquid crystals, what happens is that the orientational symmetry is broken and the translational symmetry is partly broken. Okay, but in the orientationally disordered solids, it's the other way around. The translational symmetry is broken in the sense crystal is still there, but orientational order is not there in full force. So they are partially ordered orientationally, but ordered positionally, while liquid crystals are ordered orientationally, but partly ordered translationally. So that's the difference. And here it is shown in pictures. So an example of multiple liquid crystalline phases. So on the left, there is a crystal where, you see some atoms, they are arranged in some regular lattice. Then they go into a phase, which in this picture is like a layered phase. There are layers of atoms. And so there is a layering. So properties in the Z direction show some periodicity. But in the X and Y direction, they don't show much periodicity. Okay. And so these are called layered phases or symmetric phases. And then when you decrease the density, it goes into some other phase, which is called the nematic phase, where the translational symmetry is fully restored. The system is translationally invariant. There is no layering, but there is still orientational order. Okay, so molecules are preferably in one direction than in another. And in isotropic liquids, the orientations are also random and the positions are also random, and there is no broken symmetry. Okay, and so these are the different phases. Now I come to the other case, orientationally disordered solids. So I already said that many molecular solids of non-spherical molecules on freezing first form a phase where the centers of mass of molecules form a lattice, but the orientation of molecules are random. Okay, so that is why they are called orientationally disordered crystals or orientationally disordered solids.
Can I ask a question?
Sure.
So, so you spoke about many phases, for example, liquid phase also had various different kinds of phases in them, and you characterize them by the symmetry or the lack of symmetry of
Yes,
that material.
yes.
But what are the broad characterizations? What would I call a solid, a liquid, a gas mathematically? Is there such a formulation?
Uh, I don't know about mathematically, but
Either way, yes.
yeah. So in mathematics, what happens is that you give a definition, and nobody has to argue with the definition. And but is it a reasonable definition? So that is a good question. But what happens is that solid, liquid, gas are words which are in common usage. So when I give a definition, it should agree with the conventionally accepted meaning of the word. So this is okay, fine. But now you have multiple phases. So I will show you that there are systems in which there are 4 or 5 solids, 5 crystalline phases, 2 or 3 different liquid crystalline phases. Then giving each of them a different name is an issue, it's a problem, but we will have to address it, we will address it. But it's not going to be a simple classification like solid, liquid, gas. It will be solid 1, solid 2, solid 3, liquid 1, liquid 2, liquid 3, and so on. And so there'll be multiple phases, and it is a good question. Okay, is there a good characterization for all of them together? And we will address it. And the answer is that it's not given in terms of one order parameter, but in terms of a function P of theta, which is the distribution of orientation, you take it as a quantity. This function has different behavior in different phases. Okay, so that is the definition. Okay.
Thank you.
Yeah. So on increasing the temperature, there are multiple points where usually there is a change in crystal structure and orientational structure. So typical everyday materials like nitrogen gas or methane gas, they show multiple phase transition. They don't show solid to liquid to gas. They show multiple solid phases. And so they show plastics, solid phases. So this question is not an esoteric question. It is a question of everyday life and of importance. Of course, these are low temperature phases, but they are there. Okay, so here is just for the sake of making the problem concrete, there is some material, formylferrocene, and here it is plotted the specific heat at constant pressure as a function of temperature. And you can see that there are 2 sort of very sharp peaks, which eventually become delta function like. So there is latent heat at 2 points. And there is another transition in which there is no latent heat, but the specific heat seems to jump. There is a clear peak, at least in the experimental data. Okay, so we will say that the rightmost stuff here is a liquid, standard liquid. This is kind of a crystalline phase, and this is a different crystalline phase, and this is a third different crystalline phase. So the phase 3 is the low temperature crystalline solid, which is what we would expect. And the 1 and 2 are mesophases, intermediate phases.
Okay. I have a question regarding this kind of thing. So it could be this could be a stupid question. So I remember back in my school days, there's something like an anomaly of water freezing at some temperature. So there's some anomaly I remember. So is this the same kind of anomaly that you have plotted here?
So the anomaly in water is actually some dip in the specific volume as a function of temperature. It is anomaly, considered anomaly because it is unexpected. You normally expect the volume to decrease when you decrease temperature. But in water, it increases sometimes between 0 and 4 degrees. So that's called anomalous behavior. As a mathematical function, it is just a non-monotonic behavior of the volume per particle as a function of temperature at constant pressure. So it's not really an anomaly in this sense. Here, what we are encountering is singularities in the response functions. So when I change temperature, there is a specific heat which varies in some way, but all of a sudden it jumps. And all of a sudden there is some delta function peak someplace. So these will be singularities in the thermodynamic functions, as opposed to non-monotonicity of some functions.
Oh, I see. Thank you.
Okay. Okay, so this one is the same plot, same material, ferrocene, formal ferrocene. But now I'm plotting entropy as a function of temperature. And you can see that in the liquid phase, there is some entropy roughly constant. It's not really constant, but within the measurement, it's kind of constant, but there is a jump at one point. That is the jump due to the latent heat. Entropy jumps at melting. And there is another jump at melting, even bigger, from phase 1 to phase 2. And from phase 2 to phase 3, there is no jump in entropy, which is because there is only a jump in specific heat, which is a derivative of the entropy. Okay. So the curvature here perhaps changes, which you cannot see very well in this data. Okay. So now we understand that there are multiple phases between solid and liquid. And I want to make a model of these multiple transitions in orientationally disordered crystals. Okay, so we will take a d-dimensional lattice and we will put a asymmetric rotor of fixed shape at each side. So at each side there is a molecule. And in this picture, the molecule is shown to have some funny shape. And it is unsymmetrical, it's not a spherical molecule. And there is one point which is, we'll just call it a pivot point, where it is tied up to the lattice. And then it can, the orientational degrees of freedom are arbitrary. It can be oriented in different directions. And different rotors cannot overlap. That is the constraint, a hardcore constraint on the rotors. Okay, so the picture here is two-dimensional, but you can easily imagine three-dimensional solid with funny rotors at each side, and they can orient in various ways, and so on. Okay, so now coming back, connecting it to the stuff I discussed before, if you want to discuss the solid to liquid transition, the crystal has to go away in the liquid phase. In this model, the crystal will never go away. It is there and it is always, it doesn't change. So this model cannot address the problem of solid going to liquid, but it can address the question of different phases within the crystal. Crystal of type 1, crystal of type 2, crystal of type 3. So we will see phase transitions in this model. And they are models of the different phases within the solid, within the crystalline phase, within the crystalline sets of phases. Okay. So very good. So this is the hard particles. And just, you know, the general shape is hard to deal with. So we have, for simplicity, we consider some specific models. And one of the models is this, that you have a 2D lattice. At each point, there is a rod, which is fixed at the end. And it can rotate freely, but they cannot overlap. So in 2D, that is a possible model one can study. It's one of the simplest. The second model is the same model, but now the rods are pivoted at the center, not at the end, but at the center. The qualitative behavior of this model is somewhat different from A. And C is again very similar. So it is again, you have a lattice. We are, in this case, we are just taking 1D lattice for simplicity. And then, but the lattice is zigzag line. Instead of a straight line, it's a zigzag line.
Hello.
And at each side, there is a centered rod. And we look at the, you know, now.
So can you hear me?
Sorry.
Yeah. So in the picture B, so you told that there's a hardcore constraint that the rotors cannot overlap.
Yes.
But in the B picture, it seems like they're overlapping.
No. So that dark lines are the rods, and the light lines are just the background lattice.
For the B, picture B.
For in the B. Yeah. So it's a general configuration which is not allowed, but you know, it's a possible configuration.
I see. Okay.
Yeah, and we can also study, and we do study the problem where they are allowed to overlap, but with finite cost. Okay, so that's a more general model. And so here there is an angle phi, which is the angle between rods, which is, so the zigzag angle is the parameter which is of interest. and shows different structure. The behavior of model B and C is slightly different. That is the reason for introducing them. And D is a sort of more aesthetically pleasing model. So you have here the particles are actually spherical, disks, 2D disks. You can take higher dimension, but they are harder to study. Circular disks, but the pivot is put at an off-center position. And then the pivots are on the lattice, and these things can rotate. And then you look at configurations. And interestingly, these configurations look very much like the configuration of hard sphere liquids. That was the reason for introducing them. But these are not hard sphere liquids because, again, there is a background lattice which doesn't disappear. So if you actually look at the average density in this model, in various parameters, then you will still see periodic structure because that is the background lattice. It will not go away. Okay.
So just to be clear about your last model,
Yes.
they're all these spheres are centered at the same point, and then
No,
they can
on
rotate
different
about
points on the
on the
triangular.
lattice. Yes.
Yeah.
Okay.
Okay, so before we get lost into the details of the results, so I would just like to summarize qualitatively the points which we like to make. So first is that there is an equivalence of one of these, the discrete model, this model I defined above, hard rotors on a lattice, to the set of dimer problems for some range of densities. So the parameter to vary in this case is the size of the atom versus the spacing of the lattice. If you take the spacing very big, then you have some behavior. If you make the spacing smaller, then they overlap more strongly, or they can overlap more strongly, and then you get a different behavior. And the phase transitions are driven by this density ratio, if you like. Okay. So this is the first point, is that there is an equivalence to dimer problem, which is a well-studied problem. And so it actually allows us to get some results about this model, which is non-trivial in this case where you can solve this problem. Second is that you actually see multiple phase transitions in the hard rods models, one of all these three. You actually get an infinite number of phases, distinct phases. And these can be seen in the entropy per side. They are thermodynamic phase transitions. They can be seen in the entropy per side. And the third point is that we can actually show that the distribution function of orientations has some singularities as a function of orientation. And these singularities are robust, and they can be exactly, their positions and nature can be exactly calculated. Okay. And so before I go on, this is just a picture of the results, what we get. So this is the angular distribution P of theta as a function of theta for different spacings. When you change the density, then the nature of this P of theta changes. So when the spacings are very big, then the atoms cannot overlap at all with each other. They can just rotate freely. And the P of theta is just a constant. It's this flat curve. Then if you decrease the spacing, they overlap a little bit, and you find a different behavior, which is sort of, there is some flat part and there is some non-flat part in the function. And the position of this flat region changes as you change the spacing. But anyway, sometimes this flat part disappears. And you see this curve like this orange curve here, which has some peaks at different places. Okay. And then you change the spacing more. And these peaks, which are in the second plot, this peaks is shown as green. And then you change the density and it becomes a dip. So there is a spectacular qualitative change in the behavior of the distribution function at some point. And this value of this point where the change occurs, we will be able to calculate. Okay. And okay, so there are many such changes. And sometimes there is a flat region, sometimes it disappears. Then there is this cusp, and something happens. But here, there is a behavior which is shown at even higher density. So there is the lowest curve which you see, there is the light blue curve, which is symmetrical. So there is some dependence on angles, but the position, the curve is symmetrical between this pi by 4 and 3 pi by 4. Okay, but when you change the density further, then it doesn't remain symmetrical anymore. So this is a symmetry breaking transition, which is of the type people have studied before in the Ising model and so on. It's a conventional symmetry breaking transition, while these transitions above, the symmetry was not changing, it was the qualitative nature of the distribution which was changing. Okay, and so you get one peak instead of, there are symmetric peaks and there is one peak and the second one is a smaller peak. But now if you change it even further, then if you look at this one part, it was symmetrical about the middle point, and then it becomes unsymmetrical about the middle point. So there is a second symmetry breaking transition. Okay, so, and of course we haven't plotted further, but if you go to further, there might be even more symmetry breaking transitions like this. And we are arguing that there is actually an infinite number of such transitions. Okay, so that is what we would like to see. And so here, it's the L is the length of the rod and A is the lattice spacing. And here what we are varying is kappa, which is the ratio of these two parameters. Okay, so this just
what is this P of theta?
P of theta is the orientation probability, that the probability density of the orientations in equilibrium.
Okay, and this A, B, C, D is corresponding to the figures A, B, C, D that you showed, or?
Yeah, they are just different ranges of K. In one range, you see this behavior. In another range, you see this behavior. In third range, you see that. If I put all of them in one plot, it will be too confusing. And it
right. Yeah, thank you.
Okay.
So when you said that these different values are computable, do you mean that there are algorithms which will converge to the value, or do you mean algebraic expressions?
In other cases, we don't have a formula.
Okay.
Okay, so in some cases, the position of the singularities and even the point where some singularities occur, we can calculate exactly. In other cases, we cannot. The model is not fully soluble, but some properties can be calculated exactly. Okay, so now we come to the equivalence to the diamond model. Okay, so I take a general d-dimensional lattice. There is an orientation of the particle at one side. That is specified by a rotation matrix. We call it SOD, special orthogonal group element. No? It's a rotation group. Element of the rotation group specifies the orientation of the matrix from a reference configuration. Okay, and now eta AB is an indicator function, which is 1 if rotors say side A and side B overlap. And of course, you know, this is bad notation, but I should have written eta of A and MA and B and NB. So you have to give the sides, you have to give their orientation, then you have to see if they overlap or not. But I'm just being, you know, for the sake of compressed notation, I write AB and don't write MA and B explicitly, but they have to be specified for eta to have a particular value. Okay. And then the partition function is you integrate over all orientations, and 1 minus eta AB just says that nothing overlaps. Okay, and the normalization is picked so that this integral over the orientation by itself is 1. Okay, and then this is the partition function. It will be exponential in the number of sides, and so you take log Zn and divide by n, take the limit n goes to infinity. That's the entropy per side, and that is a function of L by A. It's just a function of the internal intensive parameters. And there is only one parameter in this model, which is L by A. Because we have taken the hardcore constraint, there is only one variable, which is a geometrical problem. There is nothing like temperature. We will be able to introduce temperature later, but right now it's not there. Okay, so n is the number of lattice points, L is the maximum distance of a point of a particle from the pivot. So, you know, it's an asymmetric particle. The farthest distance up to which the particle extends is called L. That's the definition. And so in this picture above, that will be the distance from here to this end. That will be L. Okay. So for thin rods, the minimum spacing you can make is actually as close to 0 as you like. Because you can always put, the lines are infinitely thin, they can be put parallel to each other, and any spacing A is allowed. Okay, so SL by A will decrease to minus infinity as A tends to close packing limit in general. Because at close packing limit, there is only very little volume available for the system. This is just a point which is, right now it's a mathematical point, but the cases we studied before were where discrete models, where entropy is a positive function and now entropy is a negative function. It's the normalization issue.
So just intuitively, sort of I would expect that if the spacing is larger, then all the particles are free to move, all
Yes.
the rods are free to move.
Yes.
So in that sense, I would think that the entropy should be large. But
The largest value possible is 0, and it is 0. So it says that if the spacing is bigger than 2L, then particles are overlapping, non-overlapping, and S is exactly 0, which is the maximum value possible.
I see.
So I think your intuition is correctly right, and just fixing up the notation.
I see.
Okay.
Sure.
Okay. So it's just important to realize that this entropy as a function of, we will hold L fixed and vary A. So the molecules are fixed shape. This doesn't have to be a convex function of A, because all sides, the A is the lattice constant, and the whole lattice is either expanded or contracted together. And you cannot do it such that in one part there is one A, in another part there is another A. And if you go back and look at the proof of convexity, it involves this Maxwell tangent construction, which involves saying that in one part there is density ρ1, in another part there is density ρ2, then you can get any intermediate density or some such thing. That kind of argument is not valid in our setting. And so this Maxwell tangent construction doesn't go through. And SL by A is not necessarily convex function of A. In many cases it could be, but it doesn't have to be everywhere. Okay. So now the at most one overlap condition. So consider first pivots placed asymmetrically on particles so that there is a unique point at maximum distance. Like the first picture I showed, there was a unique point at maximum distance. Now suppose you decrease the distance between particles slowly. Then when the distance is just, they can slightly overlap. Then it happens that if there are these two centers, and this particle can orient a little bit, this particle can overlap a little bit, and they will overlap if this one is more or less in the direction of the second particle, and second is more or less in the direction of the first particle. Okay, so there is a set of orientations of the first particle which allows you to overlap with the second one. If the set of orientation of the first particle is outside this value, it will never overlap with the second one at all. Okay, so we say that there is a set omega-1 of directions of which allow you to overlap with direction 1. Okay, and so there is a range of spacings such that any rotor can overlap at most with one rotor in any configuration of orientation. So if this particle here can overlap with one here, it cannot overlap with the one here or there or there. So in any configuration, one particle can overlap with at most one other. Okay, so then if I take some sites I, j, j prime, and they allow all possible orientations mi, mj, mj prime, then you must have eta times eta equal to 0, because one of these two must be 0. It cannot overlap with both. So that is the mathematical statement of the no overlap condition. Whenever you have two etas, they become 0. This is an identity.
So here you are assuming the rotor is strictly asymmetric, because if it is disk, then
Yeah. So it says asymmetric. Yeah.
Okay, I see.
Asymmetric.
Right, yeah.
And we said that there is one point which is maximum distance. Okay, so for thin rods, you can easily check that this at most one overlap condition is actually satisfied in a reasonable range of distances. Between root 2L and 2L, it will be beyond 2L, there is no overlap. Between root 2L and 2L, there will be at most one overlap only. Because it overlaps here, it cannot overlap in the perpendicular direction. Okay. For other cases, you can take other lattices and all that kind of stuff. This value where this one overlap condition holds is easy to derive. It's not a difficult problem. Okay. Okay, so now we have to come to this calculation of the partition function. I have this product over integral over multiple integrals and product over 1 minus eta. So I expand this big product and evaluate each integral term by term. This is the standard thing which is done in Mayer expansion. But in Mayer expansion, the terms very soon become very messy and complicated, and there are all these stuff in textbooks on Mayer theory, which you read in books. But it's hard to explain them to an undergraduate student in a class. There's a lot of algebra is involved, and there are reducible diagrams and all kinds of stuff. But here it is very easy. Whenever you have two etas which are on the same side, they'll give 0. So the only contributions which contribute in the end in this sum are the ones which are shown in the picture below, where at any side there is at most one bond. So, sorry, there is a transcription from here to here, where I draw a red bond whenever I put an eta, and I don't draw a bond when I don't put an eta. And all the possible terms here correspond to all possible values of placing red bonds on the lattice. And any place where two red bonds come to the same site are disallowed. So then these configurations become dimer model configurations.
So you allow monomers as well?
Yeah,
in your model.
monomers have to be
monomers. I see. So if it is maximum density, then you would even then.
Yeah. Maximum density there'll be no monomers by definition.
Yes.
That is not a particularly interesting case for us here.
I see. Okay.
So anyway, so this partition function, of course, only these terms contribute. What was the value of these terms? Each of these terms is actually straightforward because these are decoupled integrals. And the answer is just z to the power n, where z is the number of dimers. And the value of z is this double integral of eta. It is the first Mayer integral, if you like, in this problem. And so the full partition function is omega r z to the power r. And z is this integral. And so this is the reduction of the problem to the dimer problem. The important point here is this. We started with a model in which the degrees of freedom were continuum degrees of freedom. They were matrices O n. But they have been reduced to the dimer counting problem, which is a discrete problem. And all the continuum integrals have been done exactly. Okay. And one should also note that this z is an integral like this, but it has a negative value. So of course, negative z is not particularly liked a priori by physicists, but by now people have learned that you have to analytically continue most of the results into negative and complex values of z. And so that is what we will be doing as well. Okay, so this is the general dimer problem, incomplete coverings, and it is not solved exactly for any non-trivial graph. And by non-trivial is meant that anything you can solve, we call it trivial, which is fair, I think. Okay, and so if the probability of a randomly pitched site is covered by a dimer is rho of z, which is this derivative. So what we need to do is to determine rho of z as a function of z. That will be the solution to the dimer problem, incomplete covering dimer problem. For any lattice, there is a function rho of z, which determines the behavior of the dimer model on that lattice. Okay. And in our problem, what happens is that the exact partition function is a function of the second virial coefficient only. There is no third, fourth, fifth virial coefficient. The full partition function in our problem becomes a function only of this Z, which is a surprise for the virial problem, because all the higher order graphs are vanishing because of the AO condition. Okay. All right. Okay, so now suppose I have this AO condition, what can I do with it? So let probe dm be the probability that the rotor at the origin has an orientation near M in range dm. So please remember, these m's are perhaps some matrix variables, and dm is a suitable volume element in this group of orientations. But for our purpose, you can just take to be the two-dimensional problem where m is just an angle theta and dm is just d theta. Okay. So Zn is the partition function, is a sum of graphs which have no dimer at the origin or a dimer in the direction I. And prob m is a weighted sum of probabilities of these subsets. Okay, these different ones. And probability that site is empty is 1 minus rho by definition. Rho is the density of dimers. Rho is the density of sites covered by dimers as opposed to number density of dimers. So it, so the probability that one particular bond is covered is rho by 2d, because there are 2d different orientation. And prob m is just a weighted sum of these things. So 1 minus rho z is the probability that it's uncovered, and multiplied by 1, which is the normalized. If it's not covered, then everything is equally likely. And here is a function which depends on the orientation. It's the probability of m in the two-side problem along direction I. Suppose I know that there is one particle here, one particle here, they are overlapping. Then what is the distribution of orientations? It's a two-side problem. If you solve this problem, that is this Fi. And by this argument, the full problem with n particles is reducible to this two-particle problem. Okay. Sorry, it seems to have got stuck.
We can see the slide.
Yeah, but I cannot shift it here. Page down. Just 1 second, I will get something. Sorry. It got stuck. Sorry. Stop. It's not moving. Yeah. I think. Okay, thank you. Sorry. Okay. So let us work out this angular distribution function in a simple case. So the orientation of each rod is specified by polar angle, and it's easy to plot this eta theta theta prime. It's the overlap distribution, and it is shown in this picture here. So this is theta here, theta by pi. Theta by 2 pi, and this is y is the theta by 2 pi, theta prime by 2 pi. And if the L is bigger than 2, if the spacing is bigger than 2L, then everything is allowed. If the spacing is a little bit less, some regions are disallowed. That is where eta is 1, and everywhere else eta is 0. And then when you change A, then the red region becomes bigger, and it becomes bigger like this and like this. So for different values of A, you can plot these graphs, and hence you can calculate the integrals over eta in this 2D plot. Okay. So for any fixed value of L by A, it is straightforward to determine the fractional area of the overlap region. It may not come out as a closed formula, but at least as a definite integral of a finite dimension, two-dimensional definite integral. Okay. So the activity of dimers is the negative of this, and it gives you the following graph. You plot L, Z is a function of L by A, and Z is negative, but I plotted minus Z, it increases. So at L by A equal to 0.5, which is the place where the things just start overlapping, this Z is 0 and it increases. But at the overlap point, where the end of the atmosphere overlap condition, this thing is √1 by √2, and this value is still 0.015. It's pretty small. Okay, so the magnitude of the activity is quite small, even at the lower end of the range of A, where this AO condition holds. And so the exact value of the partition function per site for the partial covering on the square lattice is not known. But for our purpose, we know that rho of Z has a series expansion in powers of Z, and the low order coefficients can be calculated exactly. So this series is known. You can work out 10 terms of this, but it doesn't matter, because I'm going to put Z equal to minus 0.015 or something. And even Z to the power 4 is sufficiently small, so that the sum of this series is well approximated by these first 4 terms, and it looks like this. So we will just say that rho of Z can be determined numerically as a function of Z, even though we don't have an analytical formula. Okay. And then f of m, which is the orientations, you can determine also numerically by doing those integrals explicitly, and it looks like that. So just to go before, here, in some region, f is just 1, there is nothing. But in some region, it is non-trivial, where it is less than 1. And those are the regions which we showed here. In some region, it is 0. And in some region, it is non-zero. Okay. And so finally, you can express probability distribution of orientations as a function of orientation by putting in this stuff together. And this is the plots of the theoretical function versus the numerical simulations. And the point about this plot is that here I'm not doing any analytical continuation or anything. This is a well-defined problem. P of theta is directly determined from Monte Carlo, and it shows this behavior. Okay. So it says plot of P of theta as a function of theta for different sizes. Yeah, so that's okay. So now we have done this problem with symmetric pivots. Can we extend this to the case of asymmetrically placed pivots? So if you have centered rods, the AO condition never holds, because whenever there is something here and it can overlap with something here, it can also overlap with the other side. So AO condition never holds for any non-trivial range of A on a line. But then what happens? Well, I go back to the old argument, then it says that in this picture, you can have one line, then another line will be on the same direction, but not perpendicular. So if you have two Z bonds which are perpendicular to each other, then their contribution is still 0 in some range. And so the non-trivial graphs look like the picture below. Now, this problem is harder problem. This is poorly dispersed long rods on a lattice with vacancies. Okay. The exact value of the partition function of this problem is also not known. But this is not much worse than the previous case where these were dimers, but the exact function was not known. And so it is less tractable. And so also the angular distribution does not show simple separation of the direction and density variables. Because you don't get reduction to just a 2 variable problem. You have if you have a rod of length 3 here, then there are the problem is not reducible to 2 variable problem correlation, but 3 variable non-trivial 3 variable correlations in the problem. Okay. So
just intuitively again, in this case, when you have symmetrically placed rods, should I imagine the corresponding rod model in the lattice case is essentially the weight of a rod would be exponential in the length of the rod?
No, the length of the rod is fixed. The orientation go from 0 to pi instead of 0 to 2 pi because it's a symmetric rod. I will show you the picture above. This is the model B.
Right. So this is the
So
symmetric
the
model.
angles just lie from the 0 and pi because the others are equivalent.
Sure. No, so I think I understand this, but when you go from this to the almost overlap condition or something similar to that, then essentially in the like corresponding to the diamond model, which was in the asymmetric case, you would have these long rods.
Yeah.
And so the weight of the rods is exponential in the length, or
Sort of, yeah. But it's complicated function. It's not exact exponential, it is roughly exponential.
Okay.
Okay, so it's a complicated problem. It is the polydispersed rods problem, which is not very very well solved.
Okay.
Okay. Okay, so here we have done this. Okay. So the graph is these terms. And for this case, which we studied with some detail, all our results are based mostly on Monte Carlo. There is not so much analysis you can do exactly. Like in the previous case, we had some exact curve we could fit to. Here we don't have any such results. Okay, but anyway, let us go to this next point, which was infinite number of phases as a function of L by A. So this problem has an infinite number of phases. And to argue this, what we have to do is we have to generalize the Hamiltonian to the soft rods Hamiltonian, where there are rods which can overlap, but if they overlap, then there is a energy cost you have to pay, which depends on the distance between the rods and the degree of overlap. So there is a function of u of I minus j and times theta. And u is some function of distance, which gives you the interaction. If you say all the u's are infinite, then you get the hard rod model. But if u's are infinite or they are more bigger in some places and some, you can make different strengths of u's for different distances, then this is the more general model. And then the free energy is a function of all the u's. Free energy per site is a function of all the u's. And now we like to argue that this f of u is a non-analytic function of this multi-parameter u. Okay? Because suppose I take u17, one of those u's, then when the lattice spacing is such that the 17th particles can never overlap directly, then the dependence on u17 does not show up, and it shows up below. So it's a piecewise smooth function, or it's a non-analytic function of u exactly whenever this condition holds. L by A is equal to r squared plus s squared by 2. Rs are integers. And for all these places, there will be a non-analytic dependence on one of the u's. Okay, so we have this 2-parameter family of infinite phases. So these phase boundaries are independent of the values of the u's. They are just that u is infinite or not infinite. Okay, they don't change when the value of u changes. So the equilibrium phases of the system can be labeled by two integers I, r and s, where rs phase is the one in which non-zero fraction of rods overlap with another rod at a distance r squared plus s squared by 2, but not larger. So you say that the phase 10, 15 is the phase where there is a possible overlap between the 2 points which are separated by 10, 15 distance for non-infinite u. Okay, but there are some distances where they cannot overlap at all. So there is the distinction between the phases, and the value of rs will be the largest value of r and s, such an interaction is possible. Okay. So these are geometrical phase transitions. They depend on the fact that sometimes the range is big and sometimes the range is small, so that the nth particles can overlap or not overlap. But in addition, there are these symmetry breaking transitions, which we showed you before, where the symmetry of the transition changes. And these are like in the Ising, in the transition I showed above. this one, where there was a symmetry breaking transition. This transition is in the Ising universality class as far as we can tell from numerical simulations. And this transition where there is also some symmetry breaking will be similarly classified in terms of some universality classes of symmetry breaking transitions. Okay.
What do you mean by universality classes in this context?
So it is believed that if you look at this transition from symmetry to non-symmetry case, then the transition, at the transition, the behavior is the same, whatever you pick. So it's independent of the detailed values of u's, or the phase transition can be reached in different ways, but the critical behavior is the same. That is what we meant by universality class. So in the simulation, we chose ui equal to 1 for all neighbors I, but there is just a choice. And this is the same picture repeated. And you see the symmetry breaking transition, first symmetry breaking, second symmetry breaking. And this is the put together picture in which this is the temperature variable 1 by beta, and this is the K, which is the ratio of L by A. And there are some flat lines, which are the horizontal phase transitions between different phases. So I can say this phase is different from this one, is different from this. In addition, there are these other curved lines which show symmetry breaking transition, where there is a symmetry between theta and theta plus pi, and there is no symmetry between theta and theta plus pi, and so on. Okay. Okay, so now we come to the end of the lecture, sort of. The structure of maybe 5 minutes. The structure of the transfer matrix. So consider rods pivoted at the end for simplicity. Then there is an angle theta, and at the next point there is an theta prime, and there is the transfer, the standard transfer matrix formula for solving this problem will be to solve this eigenvalue problem. Integral over theta prime z psi of theta prime t is equal to this. This is the eigenvalue, this is the transfer matrix. And this is, you have to solve this equation, find the eigenvectors, find the eigenvalue with, and the largest eigenvalue will be the one which determines the behavior of the thermodynamics. Okay, and then the partition function is given as sum of these eigenvalues to the power L with some coefficients. But from the equivalent dimer problem, we know that this ZL by M is actually given by a summation like this, where it is a sum over eigenvalues of the dimer transfer matrix, which is a discrete matrix with finite number of values, finite dimension. Okay, so the second sum is a discrete sum over a finite number of values. First sum is infinite sum because this was the continuum problem. And so since these must be equal for all L, it follows that the infinite dimensional sum must be the same as this one. And only a finite number of eigenvalues lambda alpha can be non-zero. All the other must be zero, exactly. Okay, and this is the same as in the discrete case. And as a simple check, you can take the one-dimensional problem of the dimer model is exactly solvable. And the transfer matrix for the continuum problem is not so simple, but can be shown to have only one non-zero eigenvalue in this A over the G. Okay, so it's non-trivial to find a transfer matrix, which if I remind you, looks like that one. This one. This is the T of theta theta prime, some funny 1-0 function. And it's not immediately clear that its eigenvalues will have that structure. Okay. Okay, so now last point, perturbation theory away from AO condition. Now it is good to be able to do this case when AO condition is satisfied because lots of graphs drop out. But suppose we want to understand what happens when this condition is not satisfied. So you decrease it just below the case where AO condition is satisfied, then this product of two etas is not zero. And although simplifications don't occur, other graphs are material. But you can write the partition function as the sum of terms. This is the sum where no double overlaps occur. This is the sum where one double overlap occurs. This is the place where two overlaps occur, and so on. And look at the structure of this series. So successive terms in this power series are calculable in terms of correlation functions of the unperturbed dimer problem, activity Z. And so this perturbation series is special in that it perturbs about a state that's already incorporates the A-dependent position of the cusp singularity. When I change A, the position where the cusp singularity occurs changes, and that is included in the 0th order term. There is some additional dependence on A which comes due to all these other terms, which will be taken care of by the series expansion. Okay. So the contribution of Z1 is seen to vary as A star minus A to the power 3 by 2. And so you can show some result like this. SL by A is SL by A under the 1 overlap condition plus A minus A to the power 3 by 2 for A bigger than A star and 0 for less. So it's one-sided cusp of some sort. And similar argument can be developed for other things. But anyway, so here is the summary. The model of hard rotor shows a large number of geometrical and first order disorder transitions, both type, geometrical transitions and order disorder transitions. The problem becomes very simple when AO condition is satisfied. The transfer matrix has a particularly simple structure when this condition is satisfied because almost all the eigenvalues are 0 except for a finite number. And the problem with asymmetric hard disk has an interesting variation on the standard hard disk problems. It also shows geometrical transition and the coastal Thouless phase and also some glassy phases. So unfortunately that we are not discussing here now. And that was that's still work being written up. And so I will not, this is just a preview of things to come and not really discussed here. But I'm saying that the same model actually shows glassy structures and other types of phase transitions as well. And that's where I will stop.
Let's thank the speaker for the wonderful talk. And I open the floor for questions. We had plenty during the talk. Sorry for the interruptions, but yes, if there are any further, please go ahead.
Can I ask a question? So in the first few slides, you showed a simulation wherein you said that this very known phase transition between from liquid to gas and to solid that is seen. So when these simulations are performed, and you said that theoretically it is not yet shown because under specific particular interaction, these things are not yet resolved. So what kind of interactions,
Yes, you know, we can do all kinds of simulations, but the ones I showed you are about the centered hard rod problem. Lines with hard rod constraint and put centered, the pivot is at the midpoint of the rod. 2D. I think most of the simulations are on the square lattice. The particular pictures I showed are for the square lattice, but you can also do it on the triangular lattice or hexagonal lattice.
I see. Okay, thank you.
I had a question as well. Do you expect most of this behavior to be two-dimensional in nature?
No, so as you can see, much of actually the work was described in 2D, but almost all the treatment goes in toto in 3D and higher dimensions.
I see.
The fact that you can calculate the 2-point function with the probability distribution in some range, semi-exactly.
Right. So your AOO condition would transfer automatically in the same fashion, and then I guess you'll be looking at SOD instead of SO2.
Yeah.
And okay. Are there other questions? Let's thank the speaker again. And
okay, thank you.
Yeah, thank you.
Thank you, Professor.
I can